In February of 2015, just over a year and a half ago, some of the top marine biologists, geologists, Don's Rolodex of folks that are thinking about things, got together to figure out a way to represent a three-dimensional map of the global oceans. And the year and a half that followed, a team grew, and it grew by layers. Scientists from all over the world putting in their 2 cents. A lot of heavy lifting from folks at Esri. And what's become of it is now what we call the Ecological Marine Units. And I'll introduce Roger Sayre from the USGS to get us rolling with this announcement. Welcome, Roger.
Thank you, Drew, and thank you all for this wonderful opportunity to be here. It's a little scary for me because I'm posing as a knowledgeable marine somebody when actually I'm a terrestrial ecologist by training and by experience, but I'm going to take some courage and some inspiration from what Kim Akeo said about we're all the ocean hana, and so you'll forgive me if it seems like on occasion, I don't know what I'm talking about. That happens. But really, it's wonderful to be here. We're essentially launching a new resource for all of you, which we call the EMUs, the Ecological Marine Units. It's a terrific piece of work that I've been very fortunate to have been involved with Esri. And we're launching it today. It's data, essentially, and we hope that you'll find it interesting and even better, useful. My job really is to do the setup and describe why we have these, why we did this work, and a little bit on the method. And then I'm going to turn it over to Don Wright. It's sort of a tag team presentation. And so I need to do the setup and the method as quickly as I can, sit down and let Dawn take over. And then maybe she'll say the same thing. She wants to hurry up and finish with the description of the findings so that really we can turn it over to Sean Breyer, who's going to show you the data. And we all would like to see the data. A three-dimensional mapping of the ocean, that's actually the title of the paper that we submitted on Friday to the Oceanography Journal as the essential scientific defense of this work. We're really happy about that paper. How did this all get started? I'm at the US Geological Survey, and I'm also the task lead for this intergovernmental activity, which is an activity of GEO. GEO is an acronym for the Group on Earth Observations. And GEO is actually a consortium of over 100 nations, and GEO has developed a protocol for the member nations, and there's an agenda, a body of work that GEO undertakes. And I am part of it's called a societal benefit area for ecosystems, and I'm a task leader for a GEO task, and there it is there. It's Global Initiative 14. Global ecosystems. And let me just read you the task language right here. Develop a standardized, robust, and practical global ecosystems classification and map for terrestrial, freshwater, and marine ecosystems. I have the great good fortune of doing that for my job at USGS. It's hard to believe sometimes that they allow me to do this work. And I certainly can't do it, and I don't think USGS or any of the agencies can do this without the help of Esri. So we're very fortunate to have Esri involved as a data developer partner. A great set of colleagues. Anyway, I'm the task lead for this. It is part of a GEO bond, the GEO's Biodiversity Observation Network, and the GEO Ecosystems Societal Benefit Area. And if you were here last year, we stood up on this very stage and we sort of threatened you that we're developing EMUs and you'll see them soon. And actually last year, I went immediately from here down to Mexico City for the GEO plenary. And there, Secretary of the Interior Sally Jewell announced to the world that in fact, USGS and Esri are developing a new map of standardized global marine ecosystems. And now here, 1 year later, we're launching that effort. So we're very excited. Let me tell you about it. It's not the first ecosystem map that we did together, USGS and Esri. We started on land. Land is a lot easier. We called those ecological land units, and here you see on the right a publication that we made that describes those ELUs, and I encourage you to take a look at that. The way that we did this is we conceptualized and defined ecosystems as unique areas on the landscape with unique bioclimate regions, landforms, lithology, because the substrate matters, and then the vegetation that was associated in that unique physical environmental setting. And we picked those three, climate, landform, and lithology, because they are, and if you're a terrestrial ecologist, this is familiar to you, those are sort of the primary drivers, the environmental controls on the distribution of the biota. And then the land cover actually is a biotic response to that physical environmental potential. So there's a little bit of minimum setting here in boiling down ecosystems to unique areas of climate, landform, lithology, and vegetation. But we did that, and so we had to map each of these input layers globally. And so we did that, and we did all this work at a 250-meter spatial resolution, which is pretty fine for the whole planet. And we then, in classic GIS thinking, we then combined all of these, and we got thousands of unique combinations of those 4 input layers, which we then aggregated into our nearly 4,000 ecological land units. There's the map of them. The interesting thing is you might look at that graphic and say, oh, that looks just like a satellite image. I've seen thousands of those. And in fact, it's not. That's a thematically modeled picture of the Earth, which is really striking to me. And we had some great cartography with this effort to get us into this symbolization. So those were the ecological land units. We finished those. Again, Esri was key in developing that resource. Those are available, and you're going to see them again with the EMUs, because wherever there's land, now we have the ELUs there as well. To do the EMU work, we did meet in February of last year, as Drew mentioned, and we invited lots of great international marine ecosystems, marine ecology specialists. We really have a great team. Most of these people are authors on the publication as well. There's a lot of real strong intellectual firepower from Esri. We have so much Esri support on this. And then we had some really great colleagues. Mark Costello, who's here with us, has been fantastic. We sort of consider him as a marine ecology compass for this work. And if we can pass it by Mark, then we feel it's probably pretty solid. And then Peter Harris is another one of those from Grid Arendal. And then we have Kathy Gooden from NatureServe. Just lots of really fantastic. There's Pat Halpin, folks helping us to think this through. We got together in February and we said, we need to create these EMUs, following on the ELU concept of what are the drivers in the ocean on marine species distributions. We had to figure out how we were going to do that and then get a plan together to actually produce those. And then we had some other folks joining us as well. Maria Kavanaugh from Woods Hole has been fantastic to work with. And then we had the great fortune as well of Noel Cressy joining our team, who I've heard Jack call sort of the world's best spatial statistician, wrote the book, I think, on spatial statistics. Noel has been really helpful, and he's worked with Kevin Butler, who's here somewhere, who's Esri's extremely knowledgeable and capable statistician. And Kevin did all the clustering, which is really a ton of work when you see all the data that had to go into that. So we're very thankful, Kevin. Who wants one, and what are the applications? How might they be useful? I do have to admit that this is a little bit of a case of build it and they will come. I mean, I had the charge to do this. I have this UN level commission to do this work, so I have that authorization to be able to do the work. But it's not like all manner of organizations were lining up and clamoring, we need this global ecosystems map. But then when you think about it, this is a resource that is intended to be useful for so many of these different communities. Geo and GEOS, of course, from which it comes. And in Geo and GEOS, there's a lot of thinking right now about essential biodiversity variables. And there's thinking outside of GEOS as well on essential ocean variables. And if we have mapped ecosystems, marine ecosystems, then one of the EBVs that we can address is the ecosystem extent and fragmentation. So the EBV community can get excited about this work. And then a number of other groups. And the Mission Blue folks are here. And they have the Hope Spots concept, which I'm sure you're all aware of and we'll learn more about here. And they're interested in the EMUs, and we're interested in supporting them. And we feel, for example, that the EMUs might be useful in helping them characterize the currently nominated set of Hope Spots, plan for additional Hope Spots in that network, and then take that concept away from sort of the EEZ and large marine ecosystem coastal boundary out into the open ocean, and as well to go deep, because we've done everything in true 3D. And then finally, probably the most important reason that we can help Mission Blue and all of you is we have created a standardized geospatial framework. It's the platform that matters, because we've tessellated the ocean, and we've got points on which you can hang your own data and do your own analysis. And so the very platform itself is really intended to be useful. There are all manner of applications. I usually tell people that the big ones are climate change impact studies or other disturbances to marine ecosystems, ecosystem accounting, because these days the economic and social value of ecosystem goods and services is a real hot button topic. And then, of course, conservation priority setting and marine protected area network design. And then, of course, there's other research and management applications as well. So we feel that, and we've designed these EMUs to be useful for those sorts of applications, and there may be many others that we aren't even imagining, we hope. How are the EMUs different from what currently exists? Mark put together this wonderful graphic to show you the sort of variety of different past efforts by people who partitioned the ocean for any number of different reasons. Our EMUs are different in these ways. Essentially, they're globally comprehensive, they're objectively derived from data, and they're true 3D. They're sea surface to sea floor. So those are the distinguishing features of these EMUs. Data derived is important. This isn't just interpretive mapping where we've decided to draw the line here. This is letting the data speak. So these regions are bounded by the clustering that we conducted. The source of the data is NOAA's World Ocean Atlas, the 2013 most recent version. That is a fantastic public domain research. It's really a 57-year archive of the marine, chemical, and physical environment. There are these 8 parameters in the World Ocean Atlas data set, and they've been in the public domain. And if you're a scientific researcher, you may have used these all the time. I know somebody who says, "Oh, I use those data all the time." But the normal use would be to pick your geography of interest, pick your depth, pick your time slice, and then pick your single parameter, temperature or salinity, and then go in, and then you can make a map of that sort of single feature, single point in time. And so we've done something very different, which is take the entire set of data. We didn't use these last 2 because those are oxygen derivatives off of dissolved oxygen. And so we took these 6 physical and chemical environment parameters, and they exist in 52 million points in the ocean, and we clustered the ocean into 37 EMUs, and you're going to see those. The data structure of the World Ocean Atlas data, there are points, and there are the XY dimension, the horizontal dimension is 1/4 degree. That's about 27 kilometers. Kind of coarse, but when it's for the whole planet, that's a pretty fine resolution globally. The Z variable depth, they are as thin as 5-meter slices near the top, down to 100-meter slices at depth. And so there are 102 depth zones worth of data. That amounts to over 52 million points, regularly spaced points, and in 3 dimensions, top to bottom, with that resolution that I just described. And what we did is we took the temporal data are as seasonal, annual, and decadal temporal resolutions. But we are trying to map, and this is hard because everything moves in the ocean in space and time, but we're trying to conceptualize persistent, large global water masses. And so we took the 57-year average, the life of archive average for those points, and hung those on our ocean mesh 3D point framework that we created for the ocean. So we have 52 million points, and the job was to then cluster those points in 3D. And so you have 52 million points and 6 variables on each one, and then we ran that through a k-means statistical clustering, and we got separation of the ocean into these 37 EMUs. A cluster is an EMU. So we got 37 EMUs that clustered out, and some of those actually were very small, sort of coastal freshwater influenced units. And we have 22 of those that actually occupy most of the ocean volume. And so that is a result, and Dawn is actually going to take the results and show you in greater detail. So I think this is the point where I'd like to turn it over to Dawn.
Thanks, Roger. So I'm Dawn Wright, Esri Chief Scientist, and I've been very pleased to be the co-leader of this project along with Roger. And so it's my great pleasure to share with you the results. Roger has gone through the reason for this project, the methodology. He's taken you through the data structure that you can see here in a different view in terms of the World Ocean Atlas structure in terms of the data, but also the different attributes that we are attaching to these clusters. And in terms of what a cluster looks like, we have the top, the surface area, the bottom, and within that, the volume and the thickness. So these are units that do have a volume and a thickness. This is very, very important in terms of our foray into true three-dimensionality in the ocean, which is something that Tiffany Vance and many others have been pounding on us for many years to try to achieve, and we're getting there. with every step of the way. And then our next step beyond that is, of course, to get into Nick's world of virtual and augmented reality, which is not that far off. So one of the things that is very important about this is indeed the results. So the next few slides are going to take you through the actual results of what we have. These are going to be available to you. I think they're mostly available today, and Sean will take you through the parameters of that. But one of the wonderful things that Sean Breyer, Kevin Butler, Keith Van Grafflin, and others on that particular team have done is to do a summary sheet, really a data sheet for each of the 37 clusters. And you might be thinking, why 37? Because the data told us so. The data have actually, as Roger has already explained, organized itself into these 37 units. I'm going to show you just two of them with an example of how we are describing these EMUs so that you as an oceanographer or as a resource manager or even as a child doing a high school project can understand what these actually mean. This is EMU 8. They all have numbers, but they also now have technical and common names. The technical name comes from very close association with CMEX, the Coastal Marine Ecosystem Classification Standard. That is an FGDC, Federal Geographic Data Committee standard. The CMEX perspective has been very, very important here, and I want to give a shout out to Kathy Gooden, especially because on our author team, she has represented CMEX to us so clearly and so skillfully so that we could take that perspective into actually giving these EMUs not just a number, but a name. And as Roger says, to name them is to own them, and certainly to be able to relate to them and then use them in your particular area of interest. Now, if you look at EMU 8, this is a nice map that shows you the global distribution of that particular cluster. And the colors here show you the thickness of that cluster across horizontal space. We're looking at things, of course, in 2D, but in a few minutes you'll see things in 3D. Of the parameters that Roger has already shown to you, these are the general statistics of those parameters. So this particular cluster has commonality in terms of the temperature, salinity, dissolved oxygen, and the nitrates. Again, there is a minimum, mean, and maximum thickness of this particular cluster or this unit. There is also an indication in terms of the volume. What is the cubic kilometer volume of this unit? And in relationship to the percent of the global ocean volume. So this is a very interesting unit. It is, I'll go to just the common name here. This is fairly shallow in the water column. It's cool, it's got the normal salinity, and it's got the moderate oxygen and reasonable nitrate, phosphate, and silicate values. And it makes up about 1.92% of the ocean's total volume. So this is one example of how we are describing these as data sheets. These are appendices to the article that Roger just mentioned that we have just submitted. So this is a normal epipelagic EMU. And along with this graphical map description, we are also showing you the data, the actual World Ocean Atlas vertical profiles of the 6 major parameters, and in addition, how that surface area changes with depth. So this is also very important, again, for the standard oceanographic expression of these units, but also with both the technical name and the common name. Now, if we go to another EMU, this one is a deeper EMU. This is EMU 13, lucky number 13, since we're just getting past Halloween. But it's also an example of a deeper unit. So this is a deep, very cold, normal salinity EMU. You can see that it is much larger. It covers a much larger area in the world's oceans. Again, these colors, as they get darker, show you the thickness of this particular unit, and also the numbers in terms of the 6 parameters. It's a larger volume. About 25% of the global ocean volume is taken up by this particular bathypelagic EMU. So I've shown you EMUs 8 and EMUs 13. Here is EMUs 13's vertical profile, so that again you can see the extent of these measurements from the World Ocean Atlas. And moving forward from that, we can then allow people to understand this in a static form, but how about exploring this for yourself? So one of the products that we've been pleased to release as part of this project is what is known as the Ecological Marine Unit Explorer. So this is a web app that allows you to actually explore the data from the World Ocean Atlas in the context of the clusters that Roger has described to you, and that I am now showing you in terms of these vertical views of the water column. In the Ecological Marine Unit Explorer, this is the interface, and you can immediately see this at this particular URL. And this is also being developed as a web app as well, so that you have access not only on your desktop with the browser, but also with your phone or your tablet. And for you educators, please go to this right now and start using it, because it's a fantastic educational tool, just in terms of being able to pick one spot, any spot that you would like in the global world ocean. In this particular case, we're looking at near the middle of the Atlantic. We have landed here on EMU 24. If you look at what this looks like, if you drill a geographic spike through this particular point and look down into the water column, and then explore that geographic spike through any of the 6 variables that we have described to you. In this case, we're looking at dissolved oxygen. This is giving you that vertical profile. And as you move through the water column, you can see not only EMU 24, but also the EMUs that are below that. And of course, with the ability to look at the vertical profile, you can see the gradients. If you're looking at temperature, you can see the thermocline with salinity, the halocline, and so forth. You also have the name, the technical name of this particular unit. This is a euhalene oxic warm to very warm epipelagic with low nitrate, low silicate, low phosphate nutrients, and all of the actual data parameters. So I hope you can see where we're going here, that this is very similar to the ELU method of naming, where according to the physical parameters and the response, the ecological response to those physical parameters, that is the name. And hence this is something that can work alongside the other efforts, such as the meows and the goods and the other ways of characterizing the ocean that were depicted in Mark Costello's diagram that you saw earlier. So this is a 2-dimensional view of these EMUs, and this is part of, again, the paper that has just been submitted. Roger was the first author on this, along with the rest of us as the authors. It's going to the journal Oceanography, which is the flagship journal of the Oceanography Society. So we think that this will be a perfect place for this to appear to the scientific community and then to go on from there. And one of the things that we're actually asking several things in this particular paper by way of sharing our results. Do our results make sense? Do our depth findings, these ecological marine units at depth, are they following traditional ocean zonation concepts? So this is a diagram that many of us who teach introductory oceanography use in terms of the main divisions of the ocean environment, particularly out in the pelagic, going from the epipelagic all the way down to the abyssal pelagic and the hadopelagic. These are the different zones, the thicknesses of these units that we normally teach our students in terms of, well, this is how the ocean is structured, this is how we describe the oceans, this is where we look in terms of particular processes and in terms of communities. We expect to see certain species at the bathypelagic level. Well, what really is the bathypelagic? What do the data actually tell us is bathypelagic? And thankfully, our ecological marine units are not that far off of those typical zonations. So it's not as though we have come up with something that is completely wild or crazy or not according to the standard canon of what oceanographers have been measuring and trying to understand for many years. This particular slide, it may take a little while, so I'm going to start from this side and move over. So this is just showing you what the EMUs look like horizontally, two-dimensionally, at varying depths within the water column. So we're starting here with the EMUs at the surface, and then at 200, 400, 800, 1200, 1800, 2400, and 3800 meters. And at the same time, this is the vertical profile expression of those EMUs as they are distributed at depth, but also horizontally across millions of square kilometers of the ocean surface. And then this is giving you the cluster count per depth in terms of, well, how many of these EMUs have clustered themselves statistically at the surface, how many of them are at depth. And certainly true to form, we expect to see this kind of a distribution where we have, these are surface occurring or upper water column EMUs. This is how they shake out in terms of the square kilometer area that they're covering, both horizontally and vertically down into the water column. These are middle water column EMUs and our lower water column EMUs. Now again, this is a global study, but one of the things that's going to be very important is for these distributions to be ground truthed, if you will, with high resolution data for your own area of interest. And so we'll get into that in a few minutes. But the answer to the first question is that yes, this is reasonable in terms of what we have found is reasonable in terms of what we know, what we thought was the depth zonations in the oceans. A second very important question is how do the ecosystem units that we've come up with, how do they compare with some of the other ways of characterizing or knowing the ocean in terms of biogeographic realms? And this is part of some very important work that Mark Costello, Zinatul Basher, and others are doing, and there's actually a paper that is, I guess it's in press now, Mark, in terms of your biogeographic realms characterization, particularly drawing upon the Ocean Biogeographic Information System species abundance and distribution data that is existing now globally. Now, we have here the boundaries of some of these biogeographic realms, and then underneath that are our surface occurring ecological marine units. So there's some areas that are shown in green where the boundary between our ecological marine units in the different colors, say here between 7 and this darker shade here, that lines up quite nicely with an existing biogeographical realm boundary. And there are other places in the oceans, and certainly the marginal seas and the enclosed seas in Europe match that quite nicely. There are other areas where there's not as nice of a match. So there, for instance, here within this particular ecological marine unit that our data is showing, or are showing, it does not match with this biogeographic realm boundary that cuts across that region. So there's certainly more work that needs to be done. We have taken a 57-year snapshot of this global data set, which undoubtedly will be added to, will be fine-tuned, especially as the Argo float network across the world expands. As many of you know, especially those of you in NOAA, that Argo is going into the deep Argo. So there'll be floats that will be able to actually give us better data throughout the entire water column rather than just the upper 2,000 meters with just temperature and salinity. So I've been showing you a lot of things in 2D. Let me just give you a little bit of eye candy, which is an introduction just to whet your appetite to what Sean is going to blow your doors off with in a few minutes. But if we can go to the video, the first video is going to show you a fly-through through some of these ecological marine units, and it's going to be focused on the West Coast. So the first video is that number 1, the West Coast EMU flyby. And one of the things that you see in this particular video is that it starts off with the ecological land units also. So these are the real ecological land units here, along with the ecological marine units that are visualized here as columns. So the column visualization there, even though this is really continuous data, Sean and his team came up with this wonderful way of showing you what these look like as slices in terms of these columns so that you can see the different ecological marine units. The next video, in honor of Kimokeo, and because we are all Ohana here, family, is going to take you to Hawaii. And this was the video that was shown by Catherine Sullivan, the NOAA administrator, splashing you down into Hawaii and showing the ecological marine units around that chain of islands. Again, the columns are going to pop up to show you the various ecological marine units throughout this particular region. And as you begin to surf around this particular area, there is a different feature that is added here, which is also showing you not only what these distributions are in terms of the temperature, the salinity, the dissolved oxygen, and the nutrients throughout the water column here, but also what areas are hypoxic. So we're going to be seeing some red discs that show you the levels in the water column here that are a little short on oxygen. And of course, hypoxia is a very serious problem in our oceans, something that's very important as we plan our marine protected areas. The hypoxia is something, and all of these variables we want to be able to see on a global basis, particularly how these areas, how things mix together. This will help us in terms of how we're planning science areas to target. There's also the idea that's been put forward that for a particular ecological marine unit, we will hope at the future to be able to see how that ecological marine unit changes after a hurricane or an oil spill or some other event. We're going to see changes in these parameters, hypoxia included. So this is actually a visualization that was taken from ArcGIS Pro, and you'll see this. You'll see more of this with Sean's demos. Another part of the work that is going on here is not only GEOS, the Global Earth Observation System of Systems, but AmeriGEOS for this hemisphere of the planet, for the Americas, and the Marine Biodiversity Observation Network work that is going on in our particular region of the world here. And there's a pole-to-pole map of the Americas marine ecosystems. That is another commission as part of this work, and Roger is leading the charge on that. So the ecological marine units will be, and this was probably discussed when you were in Mexico, Roger, last. And hopefully will be discussed at future GEOS and GEO meetings. Now, data products, we immediately are asked, okay, how can I get this? How can I access this? I want this for my research. I want this for my teaching. I want this for conservation efforts. How do I use this in the classroom? How do I add to this? How do I help you to improve this? I don't see that my particular study area is actually featured in terms of the level of detail that I would like to see it at. This is, of course, a global effort. But these are the various data products. I won't go through all of these in great detail. Sean is going to talk about this during his portion, I believe, but we're separating this in terms of the open access, immediate downloads of the actual data, such as the 3D point mesh. You can download the 52 million point mesh, or the 3D EMU clusters that are optimized. There are about 3.9 million of those. If you want just the top or the bottom two-dimensional ecological marine units, that is available for download through ArcGIS Online. I've already talked about the Ecological Marine Units Explorer web app that you can go to immediately. The source code from the app, the data sheets that I showed you for EMU 8 and 13. We've talked about the peer-reviewed journal article going to oceanography. There will also be a USGS AAG technical report that will go to every attendee of the next AAG annual meeting. In terms of connected versus offline for Esri platform users, this is open access for all platforms, all users. But in terms of those of us who are in the Esri ecosystem of software, these are the connected and the offline data products. Finally, what is coming up next? Certainly there are additional data. People also oftentimes ask us, okay, so where are the whale tracks? Where is the actual ecological data? That is coming. What we are working from here is the premise that we are structuring the physical environment that is what the ecosystems or what the critters respond to. So we're laying that foundation in terms of this platform. And interestingly enough, those physical parameters are affected by the ecology as well. But certainly there is the Ocean Biogeographic Information System data on the surface, more of the ocean color because there is the phytoplankton ocean color work of Maria Cavanaugh and company that is incorporated into the surface EMUs. On the seafloor, specific reef and vent features, sediment size to go along with the seafloor geomorphological layer that is already in the EMU from the work of Peter Harris and colleagues, stemming back to their work at Geoscience Australia. Roger has talked about the seasonality in the World Ocean Atlas data within the water column, so that is something that we're working on right now, as well as the direction and the velocity of currents, particularly down to 2,000 meters, which matches very nicely with the average depth of the Argo float network as well. Particulate organic carbon is a very important parameter that actually validates, further validates the EMUs in terms of their structure and distribution, and of course OBIS for the water column. In terms of tools, the 3D web viewer to go along with the 2D Ecological Marine Unit Explorer that I showed you, and to be able to do 3D cross sections. And then analysis is a very important part of this, and we again would like to give a shout out to Kevin Butler in terms of the spatial statistical analysis that he and others are bringing to bear in the ArcGIS platform. A lot of the two-dimensional spatial statistical and analytical functions are being moved over into the 3D environment. So the future is bright for all of this. And in terms of the future, we've been doing a lot of talking, and Dr. Catherine Sullivan, the NOAA administrator, was wonderful in mentioning our project and showing a video. She was briefed by Sean Breyer and Roger Sayer prior to the IUCN Congress in Honolulu, and then also Secretary Kerry's Department of State Our Oceans Conference in Washington, D.C. That was in September. We're now here in November, but week after next, I will be briefing the NOAA agency leadership and the Science Advisory Board on this project, and on the same day, Roger will be at the American Geographical Society's Geography 2050 Symposium as a keynote speaker, including this work to that very important audience at Columbia University. And then we have a scientific presentation at the American Geophysical Union in December. That's the world's largest earth science meeting with 25,000 attending there. And as mentioned before, the American Association of Geographers annual meeting next April will actually have the tech report. Everybody will receive the literature about this project, and Roger is coordinating a session where we will be presenting this work. So without further ado, I'd like to pass off to my colleague Sean to give you some real eye candy. So thank you very much.
Thanks, everyone. We'll start off by, as of yesterday, we launched this new website, and this is really the one-stop location you can go, arcgis.com/ecological marine units. And this is going to give you a location to find the apps that we have, the data downloads, and locations where we can collaborate and continue these conversations on what we can do with ecologic marine units and how they fit into the science that you're doing. We've got 3 different sections here. The first one is really sort of the overview. You heard a lot about that today, so I won't spend too much time there. There's a section on education. So Don mentioned bringing this into the classroom. We've gone through and we've built the app that they were showing earlier. I'm going to open that up in just a second. Some ideas for some lab work, and then how to get to this data for open access. Let's launch the app really quickly. Don showed this in a sort of a preview, but let's zoom in on an area of the ocean. Let's find a point. And as we're doing that, we're now sort of referencing those 52 million records and bring that into a 2D view. Right now we're seeing the temperature profile and the ecologic marine units at depth. We can actually control and look at different variables. So if we wanted to look at dissolved oxygen in that location, or if we wanted to look at salinity. So we can start now to look at any single location in the ocean, and that entire depth of data is now available. And we also do, in some cases, a combination. So temperatures, salinity are very commonly shown together. We have that capability too. And of course, then the summaries are about each one of these ecologic units. Right now we're looking at 18. If we wanted to move down in the water column and highlight the next section, we could do that, and we see EMU 24 here is 0.85%, and sort of the breakdown in the name. So that's another 2D view of how to get to the data, and this is a really simple exploration app. You don't need anything on your desktop. You have a web browser. It's going to be ready to go. We're also working on a mobile version of this, so you can actually take it with you into the classroom, have students use it, but also make it easily available for you. Let's close there. Actually, let's open this back up. One of the things you can do from the Open Data Access page is this is going to link you to ArcGIS Online. You don't need to be logged in to look at this section, but it gives you access to all the different data that we've been providing. One of the things we had to do for this data set is it was so large, with 52 million records, with 8 variables, with all this framework information. If you take the whole downloaded database, it's around 20 to 30 gig. Most people don't need that much data. They don't look at the whole ocean, so we broke it into different segments. So you'll see the Atlantic Ocean being broken apart, and we've made it available as both a desktop package. So if you're used to using 10.x, our environment, for our 2D mapping, you can download any of these and they will just open up and start to work, and they're already symbolized with the same color and information. And then in our new Pro environment, where we were looking at some of those 3D examples, you can download the same here. You also have access to online data here, so we looked at those clustered boundaries, the maximum extent of any of these surfaces. And also you have access to the app itself here. So from here you can get to really to any piece of the data set, including the summary sheet that Donna had mentioned. Is a simple PDF. This includes all 37 clusters and the maps and the associated data that goes with them. But now let's bring it into Pro. In Pro, I don't know how many of you have used it yet. It's sort of the newest desktop environment we have. It's compatible, and it's with a 64-bit technology, and it's sort of a 3D first environment. We're going to start off really quickly in the 2D map world. When you download any of these packages, you'll get this same map already ready to render. You see here, this is actually the top ecologic marine unit. We can click on this and get any of the variables. So this is truly the GIS. It's not just a mapped picture, but we give access to all the data. We can turn this off and look at specific range data. So here I've actually done a query. Actually, I'm showing the renderer here, and we have the dissolved oxygen below 1. So this can highlight those areas using the ecologic marine units. We also have added additional data. We actually see this 3D mesh as a framework. So it's not just about the World Ocean Atlas data. We can attach any other data to it. In this case, we've actually added in the color data from chlorophyll, which is a 14-year average that comes from NASA, and attached that to the surface level EMUs. We do this because we don't have depth information there, but we wanted to make this contextually available data. Then along the bottom, we do something similar. So here's the bottom unit drawing. We've taken work from Grid Arundel, which has all this geomorphology information, the kind of features, whether it's in the Hadal, and we've attached that and symbolized that data. So here, this is actually the ecologic marine units being symbolized with the geomorphology data. Now, if we go into 3D here, we have access to the same data. Let's move over here. Go to Puerto Rico today. And we're going to turn on the ecologic marine units and go into 3D. Now, the same way we were looking and pointing at the data, we have access to all the same information. Here's the name, the cluster number, the general name, or that common name that Don was talking about, and all the individual variables about each location in the ocean. So this becomes a wealth of data that you can make available and just use right into this desktop environment. And because it's the GIS data, we can actually do analysis with this. We can start to mash it up against other data. We can go and do the 3D track and see how much time a whale spent in a specific EMU, or the collection of all the EMUs that pass through over a period of time. I'm going to move to... One of the interesting things we found along the way here is we knew that we were going to get layered results from the ocean. We know with depth we're going to get changing salinity and temperature. But what we were surprised to see in a decadal data set was we see these intermixing layers down at the bottom. So these are small gaps of incontinuous layers of data at depth, but you can see as we move back through here, some of these little slivers sort of disappear over time. So these are areas where there's mixing of usually colder water and warmer water coming from the top down or from the bottom up, showing these upwellings. And you also see the coloring that's happening here with depth is we've colored the EMUs based on a color from sort of this dark pink to blue, and that represents the temperature. And then at depth, we actually darken those colors as you go through the water column. So they give you the effect of seeing this colder to warmer and the depth. And in some cases, we've had to actually add in dissolved oxygen to separate some of those colors because they were close enough that it was hard to tell. Now, let's move off the coast of Australia. And as you can see, as we move around, the colors are changing quite a bit. What happens in the water column here, there's a lot more depth of change in this water column. You can see 1, 2, 3, 4, 5, 6, 7 different layers being represented here. And here's 14 being shown, 37. And as you go up through the water column, you can see them changing. So this has become a foundation data set that we want to provide to everyone. So as of today, this data set is available. You can use it in Pro. You can download it for your desktop environment, but we're also making the summarized final ASCII data that's available. So if you need to work offline in a statistics package, you can do that, but you also have the capability of connecting directly to R to do analysis with this data, interacting with your own. So that's what we wanted to show. Any questions? There's a lot there.
Thank you, Sean. I'm sure there are a lot of questions. We weren't quite ready with the mics.
We're ready?
What's that?
You weren't ready yet.
I'm ready. But again, a hand for Don and Roger and Sean for the presentation and all the hard work. A couple of things. I'm sure there's a lot of questions that come out in the form of conversations at lunch, at the breaks. So anytime you see someone with a red badge, feel free to ask them an incredibly technical question. A couple of things here. The hands-on learning lab is going to be open from here on out. It's upstairs in the skybox, which is sort of right above the main lobby there. You have access to a wealth of Esri training at your own pace, and there are Esri instructors in there to walk you through that, so feel free to jump in there. When we break from here, when people actually start asking questions, don't ask too long, because we are all going to move outside. There should be a photographer with a ladder around, and wait for everyone. We're going to capture a group picture of everybody, so if you don't mind that. And then we'll just keep on moving across the street to the cafe. I'm assuming they're ready for us. It'll be pretty obvious where we're all going to eat. I think they set aside quite a bit of space for us. And also feel free to sneak outside and enjoy the weather. Announcements. After lunch, we have 3 breakout sessions. The agendas are on monitors outside if you don't know when you're presenting. And the folks that are presenting in here, come see Keith Van Grafflin, and we'll get your presentations loaded. There's another group in room B, where the workshop was yesterday across the way. And then there's a weather breakout in the triplex, and you'll see Jeff Donzie for that. There's Mike Wilburn, who will be in room B. So find those folks and get your presentations loaded. For those of you doing the lightning talks after the afternoon break, we'll end in here with about 9 high-paced, exciting lightning talks. It's quite a challenge to get them all out, and it's quite a challenge to moderate, but please come see me, certainly by the afternoon break, if not after lunch. And I think that's it. I'm not sure how long Nick's going to be around, but there's a lot of buzz about some of that augmented and virtual reality. Fascinating stuff this morning. Kimikeo is going to be here all day and all day tomorrow, and he told me he wants to meet every one of you. So there'll be a line forming. But remember this morning when you met somebody and shared with them how you got into oceans. Let's continue that conversation with people you don't know and with people you do know about what you are doing in the oceans and the history behind that. It's good stuff. So again, that's it for the morning session. Thanks for all the speakers. We'll see you outside for a photograph, lunch, and then presentations after lunch. Yeah.